Okay, let me start again. So I hope you all can hear me. Uh, so the idea is that we were discussing in the previous lecture one issue of standardization. So there we fixed the mean and the variance to be mean to be 0 and the variance to be 1. That's kind of standardization. The next thing I'd like to do is I'd like to understand where is the random variable actually concentrated at. So is it close to its mean? Is it far from its mean? And what we decided was in statistics is a very important question to understand what how much of the random variable is outside this interval of mu minus sigma to mu plus sigma, or mu minus 2 sigma to mu plus 2 sigma, or, there's this 3 sigma or 6 sigma nowadays, and so on and so forth. And idea. So one simple computation we're going to do is take uniform random variable between 1 and 100. And compute its mean to be 50.5. That's quite easy. The standard deviation is 28.9. Then you try and compute the basic probability. Probability x minus mu is less than sigma. So that gives you a chance that x is between 22 and 79. That's about 58 by 100. So there's about 58% chance that the random variable lies in mu minus sigma to mu plus sigma. And you can clearly see if you multiply sigma by 2, mu minus sigma is negative, close to negative, is negative in fact, close to 0. Mu plus sigma was above near 100. So mu minus x minus mu bigger than 2 sigma is like 0. There's no chance that x can be there. So in some sense that this gives you an idea of how the random variable is spread out. So in general, I wanted to ask this question: if I just give you a random variable x and tell you its mean is mu, can I somehow tell you without computing the probabilities the chance that x minus mu is bigger than k? That's what we will do now. These are very important inequalities in probability, which we will discuss, and statistics as well, which is quite useful everywhere. It gives you a first gut feel expression of what random variable do. So here's the here's the So here's the first thing. This is a very powerful inequality called Markov inequality. This is very widely used in probability. So here the idea is that let x be a discrete random variable. This random variable, which takes on non-negative, only non-negative values. Okay, which takes on only non-negative values. Okay, that means the range of x is in the positive half plane. That is, the range of x is contained in the non-negative half plane. Okay, and let's say again, let's suppose x has finite expert value. Then for any C positive, probability that x is greater than or equal to C is less than or equal to mu by C. So mu again, as before, always I just reiterate one last time, mu is always E of x. So something that one very useful. So chance that mu lies above C is always given by, at the most, by mu by C. So that's something very useful idea. One has. The proof is also not so hard. We'll just try the proof a little bit. So here, I'll write a sketch. I'll do a sketch. I won't do a precise proof. So the range of x is countable. So it's a countable subset. Countable subset of the real line, of the positive real line. because range is counted. So here I'll write mu is the same as the sum over t in the range of x. Let me call this as t. So t is the range of x, is a constant. So t in t, t times the chance that x will equal to t. Right. So now here this is the same as, so now c is some number that I have, right? So let's fix a c. Let's fix a c positive. Let's fix c positive. So what I do is I go and divide the sum into two parts. Sum over t is less than c and t is in t, plus the sum when t is bigger than c, bigger than equal to c, and t is in t. Okay. So this I do this, and I do the same thing. Probability x equal to. Okay. This is what I do. T less than c and t bigger than c. Okay. So now once I have this, again this is again a formal computation. You have to make it rigorous. So in this first one, everybody, all this t is less than the c. Right? In the second one, all the t is at least c. Right? And I know t is contained in 0 infinity. So this whole first term is non-negative. So let me erase this part. This whole first term is non-negative. So because t is non-negative and probability x equal to t is non-negative, this first term is non-negative. This first term is non-negative. So what I could do is I could just throw it away. I could say my mu, so this will imply my mu is always going to be bigger than equal to, I'll just throw this away. I'll just put this as 0 plus I'll write whatever is here. The sum over t is bigger than equal to c, right? Bigger than equal to c, the chance that t times probability x equal to t. So I'm just throwing it away. And this t in. In the second step, what I do is I observe that everybody in this sum, t is non-negative, but more importantly, everybody is above c, right? So all these t's are above c. So now I can do a similar computation. I can say this implies mu's are now again, okay, I forget the 0 is gone. I have everybody's above c, so I pull the c out, and then I leave the sum in. I say sum of t bigger than equal to c, t is in t, sorry, I should not do this. T is in t, probability x equal to, oh, sorry. T is in t, probability x equal to. Here I'll just replace the c by a c. So I remove the c outside. Okay. I can do that because every term is bigger than equal to c, so a sum has to be equal to c. Now this will imply what? This will imply now that mu is bigger than equal to c times, what is this now? This expression right here. Let me go to the next page. I'll come back to this show it again. This expression right here is just everybody above c, right? So it's a disjoint union of everybody. So what you do is you write this as c times the probability of the union of t bigger than equal to c, t in t, x equal to t. Right? That's what that is. But that's just the same as c times the probability of x bigger than equal to c. There's no difference. So that's your result. You've shown, so this will imply, let me make this a little bit smaller so you can always move a little bit higher so I can sort of do it in one page. Sorry, here is this, undo, go here, and this is. You up a little bit higher, a little bit here. Remove this also a little bit higher here. Remove this a little bit here. Remove this a little bit here. So everything is one page. So this whole thing will imply that mu is bigger than equal to c times probability x bigger than equal to c. That implies that what we want, chance that x bigger than equal to c is less than equal to mu by c. That's what you wanted to show. That's a one-page proof. So two things is crucially we use the fact that it's non-negative because we will throw the first sum away. So that's where we use the fact that the range is non-negative. That's a very crucial step, right? It's a very crucial step here. If the range is non-negative, you can't throw that sum away. And this part we use the fact that x is bigger than or equal to c. And then here we use the fact that the axioms of probability, the sum of the probability of a union of disjoint events is the same as the sum of the disjoint. That's the second axiom of probability. So kind of both these give you a very interesting fact that the chance that x is bigger than c is at the most mu by c. It can't be more than that. So if c is large, your mu by c is going down. That's sort of a So now there's sort of this only works on non-negative random variable. So sort of you might think that okay, it's sort of so we write Markov properly to give its full credit. So Markov. So you might think, okay, it's non-negative, so it's restrictive. It's not. You can't really apply it otherwise for all random variables. But it's sort of a simple generalization. So let's just do this. This is due to Chebyshev. So this is called Chebyshev Inequality. This is a very famous theorem. So what you do is you take x to be a random variable with finite variance. Okay, so finite non-zero variance. So x is a random variable. So x is a discrete random variable. Random variable with finite variance. With finite non-zero variance. So now what happens is that so then we had asked this idea, right? We wanted to know. So then for any k bigger than or equal to 0, we wanted to know what's the chance that x minus mu is bigger than or equal to k times sigma. That is what we want to understand. What is going to be there? So there's a simple bound for this. This is always going to be less than or equal to 1 by k squared. So this is a sort of Chebyshev inequality that here I don't assume anything about random variable. I just say it has non-zero variance. There's finite non-zero variance. Implies a finite mean, and this is true. So how does one prove this? Let me prove this. Here's the proof. So the trick is that you want to apply Markov inequality to a non-negative random variable. X is not non-negative, so you can't apply to x. But you're almost close by. You have x minus mu in absolute value, and that's the trick. So what you think about is the following. So x minus mu is bigger than k times sigma, right? This is what you have, right? This is the event you have. This event is the same as the event. So I want to make it non-negative and make it easier. So I'll think of it as the event x minus mu the whole squared is bigger than k squared sigma squared. So it's the same event. If I square both sides, now if I take the random variable y, which is x minus mu the whole squared, that's like a non-negative random variable. Because it's a square. And I know e of y of the random variable is e of x minus mu whole squared, and that if you stay a little bit, it's just the variance of x. So it's just sigma squared. Right? That's easy. So now I can apply Markov inequality to y, okay, to y with what? With c equal to, let's say, so I want to know the chance that I want to know, what do I want to estimate? I want to know x minus mu is bigger than k sigma. So let's fix a k. Let's fix a k. So k positive, I guess. So now I fix a c with just c by c as just 1 over k or k k. So or k sigma in this case. So then what I do, I just know that the problem take c to be equal to k sigma, k squared sigma squared. So then I know that the probability of y bigger than or equal to c is less than or equal to the mean of y divided by c. That's what it tells me. Right? So now what is c? What is mean of y? Mean of y is sigma squared. C is k squared sigma squared. So I get 1 over k squared. And what's this side? What is the chance that y is bigger than c? That's the same as, what's y? Y is x minus mu whole squared. And what's c? C is k squared sigma squared. Right? That is this half. This is less than or equal to 1 over k squared. But that's the same as the chance that the absolute value of x minus mu is bigger than k times sigma is less than 1 over k squared. That's the proof. So a fairly simple proof of the event of this property of Chebyshev Inequality. All you have to do is apply Markov inequality in a property. So it's a very useful result. So that means you know that the chance that x minus mu is above k times sigma is always bound by 1 over k squared. So it will decay. Of course, this decay may not be enough for you, but this is a decay of probability. And there are other inequalities in probability which tell you how a little bit. If you understand more and more properties about x, you can get further descriptions about how close x is to its mean. This is one simple inequality that tells you that x is within k units of standard deviation is like 1 over k squared. This is an example. Keep in mind, it's a very important inequality. So two inequalities are very important in probability and statistics. So I'll just reiterate them a little bit. Again, split view. Let me show you the previous one. So one is Markov inequality and the other one is Chebyshev inequality. So both these are very, very important aspects in probability. So one just says that if x is non-negative, a brute force estimate for the tail probability is just mu by c. So x is bigger than or equal to c is kind of the tail of the distribution. So you just say x bigger than or equal to c is like mu by c. And Chebyshev inequality says that you can quantify how far x is from its mean within some units of standard deviation is that by k squared. So it's k units away means it's 1 by k squared. Very nice. Okay. So now these are ideas about how far a random variable from its mean and so on and so forth. Now I want to also understand, if I know something has happened, how does my mean and variance change? So I just want to go back and connect with conditional probability a little bit. Okay. So here, so now I want to do this thing called, it's 4.4 in my book. It's called conditional variance, expectation and variance. friends. So here I want to understand the following idea. So before we knew that if a random variable x was given and an event a was given, we knew that the distribution of x changed with if you know that the event a happened. So for example, let's just do a simple start a simple computation. So let me do an example. Let me start with a simple example. Let's say example. So before that, let me just write down. So if x is a discrete random variable, and a was an event, the probability of a is positive. We knew that, and we knew that if like say y was the random variable x conditional on the event a, the probability of y equal to some number t was given by probability of x equal to t given a, and that's the same as x equal to t and a are divided by probability. Right? So this was what we called as the conditional uh, distribution of x given a. Right? That's how we define this whole idea. So now we know that, let's take an example, for example. So we knew that the following idea happened. These things change quite a bit. Right? So for example, let's take an example, 4.4.2 in my book, let's say. So here, let's say you roll a die. You roll a die. And let's say x is the outcome. Right? X is the outcome. Then let's say A is the event, the outcome is even. So A is the event that 2, 4, 6 occurs. Right? So the roll is even. So now we know that probability x equal to k is 1 over 6 a priori for k in 1, 2, 3, 4, 5, and 6. That's just uniform. X is just uniform. 6. But we also know that probability x given a, x equal to k given the event a, right? How do we do this? This is the same as probability x equal to k and the event a divided by the probability of a, right? Now that's going to be equal to what? Probability of a is just 3 by 6, right? So probability of a is 3 by 6, and that's a half, right? That we know. So this we know is going to be twice the probability of x equal to k and a, right? So this is what you're going to get, right? So let's say and a. So now, if you go a little bit further, this is going to be what? So now, if k is odd, x equal to k and a doesn't occur. That's a 0, right? That's 0. Nothing happens. If x equal to even, then the chances is just that number. K and a is a number. So this is a simple exercise. One can just check that this is going to be equal to just twice the 1/6. So you just get 1/3. Right? This is 1/3 if k is in 2, 4, and 6. And this is because of the fact that x equal to k and a, when k is even, this event is the same as x equal to k. Right? That's the observation you make. Let me erase the right in green properly, neatly. Oh no. Very good. So this is the idea. The observation is that k is even, then the event x equal to k and a is the same as x equal to k. And if k is odd, x equal to k and a is the empty set. That's the idea. That's what you have to use to show the result. So now you know that the distribution of x given a is very different from the distribution of x alone by itself. So the random variable changes a lot. So similarly, the mean also will change. So for that, we need to identify what do you mean by a conditional mean. So here's the definition. Here's the definition. let x from s to t be a discrete random variable. Let A be an event, in S such that probability of A is positive. So this is something we have to be careful about. The conditional expected value. So the conditional expected value is defined from the conditional probabilities. Okay, is defined from the conditional probabilities. In the same way as ordinary probabilities, as the expected value, right? In the same way, let me write differently, the ordinary expected values. Ordinary expected values. Value is defined from the ordinary probabilities. Okay, so that is, how do you do this now? So that is E of x given the event A, that is the conditional expectation of x given the event A, is defined as the sum over t in t, the range of t, such that you multiply t, and before you would put just probability x equal to t. That's the ordinary probability. But now you would put the conditional probability. So what you'll do is, so let me write this down, that is in blue. The conditional expectation of x given the event A is going to be this condition on the event that A happened. So you replace it by the conditional probabilities, not the original probability. Okay, is that clear? So the idea is that you don't use the original probabilities, you use the conditional probabilities to compute the conditional expectation of x. And similarly, so extending this, similarly, we have the conditional variance of x given A, right? X given A, that's going to be the same as you'll always use the conditional expectation again of x minus E of x given A whole square. So you use so I'll use the conditional expectation of, so I'll condition it, right? But what is inside? Inside I will put x minus, I'll always work with the condition of x given A whole square. So variance also is defined as the conditional expected value of the same way. Very nice. Right, so this is what, so let's go to the example again. Let's continue the example. Let's try and do this computation. So it's kind of clear there. Let's try and do this. So example, what's the example? The example is the previous page. Let's go to the example. The example was, I number it, 4.4.2. Let me continue it. So there what we did, I found out that so if I want to find E of x given A in that example, so what I get? So I had E of x given A was the same as the sum over t in t, just t in 1 through 6, t times the chance that, so here I would have the chance that x equal to t given a, right? That's the probability I would take, right? So x was the original random variable, so I'll leave it in black. But that we know we know it's 0 for odd and 1/3 for even, so I'll get 2 times 1/3 plus 4 times 1/3 plus 6 times 1/3. So that's going to be equal to something like 8, something like 4. 2 plus 4 is 6, 6 plus 6 is 12, 12 divided by 3 is 4. And now you can do the same thing for the variance. So the variance of the random variable of x given a, so what's that going to be? That's going to be, again, look at this formula, it's e of what's x, x is x, minus this random variable is going to be e of x given a, we found out to be 4, so this comes 4, this whole squared, given the event a, right? But this again we know is going to be the same as, so what do? You know x takes under a, x only takes even value, the odd values are all 0, so you again get 2 minus 4, the whole squared times 1/3, plus 4 minus 4, the whole squared times 1/3, plus 6 minus 4, the whole squared times 1/3. And that will give you 8 by 3. Right. So, so one interesting thing is that you should just compare e of x with e of x given a and variance of x with variance of x given a. Right. So let me just do a split view and try and understand this a little bit better in sort of global way. Let me go back here. Okay, let's come down here. Let's just tell a little bit. It's a nice competition. Go back here. 8, 7. Let's go back here. So now, if you start this off, then the idea was that if you give an event A, you know the random variable changes, and this we have seen many times before. So we understood that the conditional law definitely changes. For example, it goes 1/3 for all these guys and 0 for otherwise. And then I said that, okay, the conditional mean I defined by saying that it's just over the conditional probabilities. And the conditional variance is again the same thing over the, you take the conditional mean, you subtract it, you try and see how it differs under the conditional probability. So now you found out that this that the conditional mean of the uniform given the event A is 4. But the original mean we also know, right? E of x is just 1 plus the sum of the mean, sum of 1 plus 2 plus 3 plus 4 by 6. That's just going to be 3.5. So this also we know in that sense. We know. So this kind of it's a nice way of understanding that that the mean kind of gets a little bigger, and the variance is 1/3, but the variance of the original one is like, let me add the original one. So let me add e of x. In this case was let me go back the whole screen. So we go to the next page. We go bigger. So if you come here, then you can notice that the e of x is like before was like 3.5, right? Here it's like 4, so it's a little bigger. And the variance of x, if you did before, it's like, I think with the computation, it's I think 35 by 12. And so you know that, okay, it's kind of close by. It's not changed much, but it's a little less. But the mean kind of jumps up. So it's kind of an interesting idea. So if you give an event A, you can increase the mean, or decrease the mean if